So welcome to the paper session 7, remote collaboration, telepresence, and teleoperation. My name is Kiyoshi Kiyokawa from Narrow-Insim Science Technology, Japan. Okay, so this session has 4 excellent papers. Okay, so let's begin with the first paper entitled Exploring the Effect of Viewing Attributes of Mobile Area Interfaces on Remote Collaborative and Competitive Tasks by the Nelusha, Wattaranthenne, Marium-E, Jannat, and Khalad, Hasan, and Patricia, Lasserre. Who is the presenter? Do we have the first presenter? Hi.
This is the perception. This is perception. Perception section. This one. Is it?
Which room is this?
Is the next room?
So, okay, so maybe we can have the second paper first. So the second paper is in, do you have the second presenter? Okay, which is entitled, Does Voice Matter? The Effect of Verbal Communication and Asymmetry on the Experience of Collaborative Social XR by Patricia, Merz, Carolin, Wienrich, and Marc, Erich, Latoschik.
All right. Hi, everyone. My name is Merz, and today I present our work, Does Voice Matter? The Effect of Verbal Communication and Asymmetry on the Experience of Collaborative Social XR. This work is together with my supervisors, Carolin, Wienrich, and Marc, Erich, Latoschik. We are from the Human-Computer Interaction Group and the Psychology of Intelligent Interactive Systems Group from the University of Würzburg. Smith and Neff have shown that embodied virtual reality has similar communication patterns as face-to-face communication. So VR seems to be a promising technology for remote collaboration. However, there are use cases where someone might not want to wear an HMD, like during traveling, and there are challenges for VR like cyber sickness or discomfort in long sessions that could prevent someone using an HMD. Asymmetric collaboration allows users with different devices to interact. Therefore, users that cannot use virtual reality headsets can take part in the collaboration. For example, one user takes part with a desktop computer and the other one with a VR headset. Prior research addressed co-located, remote, and hybrid asymmetric collaboration. In this work, we focus on remote collaboration. However, for remote asymmetric collaboration, prior work focuses on tailoring the user role or the interaction possibilities of a user based on their device. For example, there are different works where the less immersive user is acting as a guide for the high immersive user. Our prior work, which we presented at the VR conference earlier this year, focused on users without predefined roles to evaluate how only the differences of the devices affect the user experience. We compared different asymmetric settings with a symmetric one to research how self-immersion and the immersion of the interaction partner affect the collaboration. When talking about immersion, I refer to the definition from Slater. So immersion is based on the device configuration and affects the user experience on many different aspects. Prior research has shown that higher immersion leads to higher presence and a higher sense of embodiment. So when users with higher immersion enter a virtual environment, they have a stronger feeling of being there and controlling a body. Further, co- and social presence, as well as virtual human plausibility, are impacted by the level of immersion. Co-presence is the feeling of being there together, while social presence is the feeling of interacting with someone else. With virtual human plausibility, we refer to the plausibility of the appearance and the behavior of a virtual human. In our prior work, we evaluated whether the immersion affects user experience in asymmetric collaboration, when the users do not have these dedicated roles. We found that higher self-immersion leads to higher quality of self-perception. On the right side, you can see the results for spatial presence. Spatial presence is higher for users with an HMD than for desktop users. However, we found the surprising result that self-immersion does not affect how we perceive the other, despite there being a lot of research for this. You can see our previous result for co- and social presence, where the values between the devices are pretty similar. We then questioned why we found these results and suspect that it was due to the missing social cues, since participants were not able to talk to each other in the previous study. However, verbal communication is an important social factor for collaboration and affects user experience. Prior research showed that including verbal communication in shared immersive experiences affects self-perception and other perception. So including verbal communication could change the findings of our previous study. Therefore, in this work, we want to answer whether verbal communication and asymmetry affect our constructs of self-perception and other perception in collaborative social XR. To answer this, we conducted a study where we manipulated whether participants collaborated in an asymmetric or symmetric setting. One condition was 2 users interacting with the same device, in our case 2 VR HMDs. The second condition was one user with a VR headset and 1 user interacting via desktop computer. The participants could talk during the interaction with each other, and we conducted a study with 52 participants, and it took about 35 minutes. For the variable of verbal communication, we took the condition of no verbal communication from our previous study, with 53 participants that followed the same procedure. Therefore, we have a 2-by-2 between subject design. Regarding the procedure, we invited 2 participants to our study at the same time. They were in different rooms to evaluate remote collaboration. First, participants got information about the study and the consent forms, and then they answered pre-questionnaires like demographics. After that, they entered the virtual environment, creating their avatar and getting used to the respective device. Afterwards, they joined the social virtual environment to collaborate with other participants on a sorting task. And finally, they filled out post-questionnaires. Our device configurations were asymmetric or symmetric. So 1 user with an HMD and 1 user with a desktop computer for the asymmetric one, or both users with an HMD for the symmetric one. In both conditions, the participants were always seated, and for the same quality of verbal communication, we used the same headset for both device configurations. This is the point of view from a VR and a desktop user during the task in Social XR. Before the task, participants could customize their avatar by changing hair, skin, shirt color, and the gender. During the sorting task, the 2 participants each had to sort 5 simple objects into virtual containers, based on the number of corners of the objects, from left no corners to right the most corners. To sort the objects into the virtual containers, the participants had to press the virtual buttons in front of them via mouse click or via their controller. Here's a short video of the task. On the left side is the view of the desktop user, and on the right side, the view of a VR user. The participants were assigned to the blue or the red side, and additionally, there were objects colored in red or blue. If a not fitting object colored appeared on their side, the participants had to press the interact button to transfer the object to their partner. Then the partner had to confirm the swap by pressing their interaction button as well, and then they finally had to sort in this object. The task ended when all of the 5 objects were sorted in. During the interaction, the participants could discuss where to place the objects. To evaluate our research question, we had the following hypothesis. For self-immersion, so whether oneself was using an HMD or a desktop computer, we expected that higher self-immersion leads to higher quality of self-perception and other perception. So we expected that the difference in immersion influences these factors in the same direction. We expect similar results for verbal communication than for self-immersion. We expect that including the social cue of verbal communication, it increases the quality of self and other perception. Let's get to our results. In the upcoming slides, you can see our hypotheses on the left side. For the plots, the bars are colored in green or yellow, representing the device configurations. And beneath the plot, you can see whether it is the condition with or without the verbal communication. First, we take a look at our result regarding self-perception. We found significant differences for self-immersion and verbal communication for spatial presence. Participants perceived higher spatial presence when using an HMD and when they were able to talk and hear the interaction partner. For the sense of embodiment, we only found significant differences for self-immersion. Participants perceived higher agency and sense of embodiment in general when using an HMD. We found no effect that being able to talk to the interaction partner affects the sense of embodiment. Therefore, we can accept our hypothesis that self-immersion affects the self-perception. Since we did not find the same results for all self-perception factors for verbal communication, we cannot accept this hypothesis. So the device we are joining with has a significant impact on the self-perception, while verbal communication only has an effect on specific factors. Regarding other perception, when looking at co-presence, we did not find any significant differences. So we found no effect that the self-immersion and verbal communication did affect whether we perceive that someone else is in the virtual environment with us together. This is in contrast to our result regarding social presence. For social presence, we found an interaction effect between immersion and verbal communication. Participants perceived higher social presence when using an HMD and when talking with their interaction partner. I really want to highlight this finding since this is one of our main contributions. This means then when including the social cue of verbal communication, the different level of immersion affect how we perceive our counterpart. So differences in social presence between the devices are only appearing when including verbal communication. Since we did not find the effects we expected, we have to reject both of our hypotheses. To wrap my talk up, let's get to the conclusion. Immersion and verbal communication affects the user experience in asymmetric social XR. So we can answer our question with yes, voice does matter, and we should accordingly design social XR applications. For example, for remote collaboration on 3D objects, users should be able to talk to each other no matter the device. But if it's possible, high immersive devices are better. Additionally, future work has to look into whether the same effects apply for different tasks. However, if one user cannot join with an HMD, asymmetric collaboration is an effective alternative since the interaction quality stays high for high immersed users, even when the interaction partner is less immersed. So the immersion of another user does not reduce the user experience of oneself, and it enables users with less immersive devices to take part in the collaboration. Additionally, we suspect that other social cues like facial expressions and avatar appearance could increase the effect of device differences. So there's a need for further research in asymmetric collaboration. And hopefully we can talk about this after my talk in interesting discussions. These are the references used in this presentation. And thank you for your attention. I'm happy to answer your questions.
Yeah, thanks for the interesting presentation. Maybe just a short question out of curiosity. So in your task, right, it was a collaborative task where people had to sort shapes into boxes. How was that even possible without verbal communication? I mean, from a perspective, right, most of the time you use gestures or facial expressions if you don't have verbal cues available. So I was just wondering how you actually used this in your previous work, right?
Okay. Yep. So if you have a look here, you can see that both users have to sort in 5 objects, and they had to swap sometimes an object when it was colored, for example, blue or red. And then they had to press an interact button, and it highlighted the other interact button from the partner. And then they knew, oh, my partner wants to swap the object. And then they can press it, and the object swapped. And then they could sort it in. So yeah, there was no verbal communication needed.
Hi, I'm Yasra from UMass. Great presentation. I wanted to ask, so the task and how the verbal communication goes, sometimes we will choose not to talk at all. Do you think if we change the task, something very collaborative, because this is sorting tasks, it doesn't need a lot of collaborating, would that help, or would that confirm your results, or it would go against it? And second, if more than 2 users are there, so at this point they're talking to one another, but if there are 4 people, who are they talking and when? Can you infer that, and would that change the results? Do you have any thoughts on that?
Okay, regarding your first question, I think when there would be another task where they had to communicate a bit more and where there would be a more deeper discussion, I think the differences of the devices would come more, would be more present, because when the social interaction is higher, which we showed when including verbal communication, the device differences are there. So I think that other tasks could influence it. And I don't think you have the microphone anymore, but can you repeat your second question? That's an interesting question. I'm not sure how to answer it. I think it really depends on the setting, how many users are using which device, and is one user not able to do an interaction, for example, in comparison to a user with an HMD. And I think then there will be, of course, device differences, but I'm not sure where your question is going when including 4 people, for example.
Okay, sorry, time's up. So let us move on. Let's thank the speaker again. So do we have the first paper author? Not? Okay, so maybe we will move on to the third paper, so which is entitled Spatial Affordance-aware in Interactable Subspace Allocation for Mixed Reality Telepresence by Dooyoung Kim, Seonji Kim, Selin Choi, and Wontek Wu.
Okay, hello everyone. This is Dooyoung Kim from KAIST Augmented Reality Research Center. I'm a postdoc researcher, and this work was conducted with Seonji, Selin, and my advisor Wontek from KAIST UVL Lab. So my title is Spatial Affordance-aware Interactable Subspace Allocation for MR Telepresence. So let me start with the motivation of the study. So when we conduct the MR Telepresence, as you can see, the remote user will be present in our space as an avatar, but if the space is not precisely meshed, like this avatar can pass through my physical objects like this. And this problem is more, become dangerous, like this in VR users, if their physical space in connected virtual space is not registered precisely. So maybe he's sitting on the virtual chair in his virtual space, but there's no chair in his physical world. So the important thing is, so the research question is, how can we overcome the spatial heterogeneity and allocate remote spaces to the target host space, so even if the number of remote space increases? So this is my research question. And it's the concept overview of the contextual mutual space generation with subspace allocation. So let me show you in each context. So assume that we conducted a table-centric collaboration in AR host space. So in this case, my algorithm will gonna find some optimal subspace like this. So find some target table area and the movable area beside them, and then they can initiate it in host spaces like this. So if it's wall-centric collaboration, the host will gonna move there, and all 2 other client users will be also allocated like this. So if it's floor-centric, they're gonna find the maximum movable area in each space and allocate them. So as you can see, all users have they can see the same host space, but the interactable space is different, so to overcome the spatial heterogeneity. And with the related works, I just introduced the interaction over spatial matching in last ISMAR, and I mentioned the importance of how we should precisely match the edge or surface that where we're going to interact with, not just focusing on the overall semantically matched ratio. But it was only applicable for VR users. There's another approach for avatar retargeting like this, but the thing is, it's not continuously mapped, so if avatar moves a certain position to other position, it can be suddenly teleported to somewhere else. I mean, it can lead to the breakup immersion. And the most common ways to make a semantic alignment between dissimilar spaces and set the intersected area as a mutual space, but the thing is, if the spatial dissimilarity increases or remote spaces increases, the generated mutual space will be really small and really narrow, which is not sufficient for collaboration. Another approach is the object-centric mapping, which is introduced in last Kite. And also, it considered the target object for collaboration, but they didn't only concern about the object, so the other like obstacles or movable areas are not considered, and the avatar's position is not also considering the spatial configuration, so they get someone like on the desk or like some weird places to which can also lead to the breakup emergence. So from these related works, my takeaways can be threefold. The first is dissimilar physical and virtual space registration, considering interaction between user and space. And the second is separate the interactive and viewable areas to ensure the robustness as the number of remote spaces increases. And the last one is considering the matched space and the spatial affordance, what users perceive in their connected space, set the instantiation position of each clients and hosts before starting the remote collaboration. So my method can have 4 steps. The first is to select the target object cluster through the scene graph. And the next is, with an optimization algorithm, figure out the optimal position of each client spaces. And the third is, considering the spatial affordance with the matched space result, figure out the optimal instantiation pose for each users. And the last is subtract each space to minimize the unnecessary obstacles or spaces are matched. So let me show you more detail. So assume that there's a host space like this and 4 remote clients from 4 different spaces access to this host space. So first of all, I extracted the floor plan with these labels. And assume it's a table-centric scenario. So this table and host space is set as a target object. And there will be several tables in each client space. But considering this scene graph, we can figure out the appropriate object cluster to be matched. So after this, the main target object in each client and host space will be set as a target object to be matched. So now we can get this pre-processed floor plan input spaces for each space. And with the optimization algorithm, it could figure out the optimal rotation and position to be matched. So if we just allocate all these 4 spaces, it can be overlaid like this. And then, considering the aligned table, as you can see, the edge of each client and host space is matched like this. And considering this, we figure out the candidate positions where the users have to be instantiated or located. And then get rid of the impossible to be spawned position. And then also another optimization algorithm to figure out the optimal position set for each client like this. So the C1, 2, 3, 4 refer to client from space 1, 2, 3, and 4. And after that, the host users, which is physically located in the target host space, will be someone like this, considering the distance and collaboration context. So as you can see, if you just utilize if you just finish in this tab, as you can see, so many discolored mismatched areas are shown. But we have to visualize all these things to prevent this object collision or the avatars invading my physical space. But if we just visualize all these steps, it's too annoying for collaboration. So the last step is, assume from the client 1 space, we make a smaller markers beside them and move around with some certain algorithm. It's all more detail is in paper. So then we can find some like this optimal subspace for each client and subtract the, so like typical VR HMD system, these boundaries will be shown as a grid to VR users, and they can all perceive this host space. So if I apply to these all 4 clients, as you can see, the unnecessary area will be minimized to reduce the unnecessary augmentation. So this is the result when I run my code in Python. So if it's table-centric, as you can see, the client's users are allocated just like beside the edge of the table. If it's wall-centric, they're all like located like this, and these colored line refer to the each clients could physically interact with, where they can get a passive feedback from their physical wall in their space. If it's floor-centric, it can be shown like this. So for validation, I compare our method with the simple this all intersecting method and similar subspace extraction method, but didn't considering the target object or context of the collaboration. So we said 4 host spaces and 10 client spaces like this. And then we make some combination with this host and client spaces. So actually, the spatial matching research is mostly consider up to 3 client spaces, but in my study, I consider like up to 6 client spaces to show the robustness for the number of increase in client spaces. So out of like 900 combination, we conducted the spatial matching. And as you can see, our method could effectively allocate in most cases with 2 or 4 client spaces. And for 6 client spaces, in 4 contexts, you can allocate all conditions, but for table and wall, it's about like 50%, but this is because of the physical size of the host space, relatively small to be allocate all 9 users physically. So which means, even if they're all physically located in the same space, they're hard to be conduct the collaboration. So compared to this, the previously most common, the intersecting method mostly fail with 4 or 6 client space cases. And also measure the total mutual area, and our results show that as client spaces increases, which means the remote collaborators are increasing, so we have to secure more wide mutual space. Which means that, so in client 2, with 2 client spaces, our system showed this interactable area. If it's increased to 4 or 6, as you can see, the area where we could utilize for collaboration increases. In contrast, the simple intersection method, as we can thought that the visual space size decreases and all failed in 6 client spaces. And since our method all clients have a different interactable subspaces, we measure the mean subspace area per client. And our results show that we can secure about 4 to 6 meters square interactable area per client. And the obstacle area was like about 1 or 2 meters square. Compared to this, like the intersection method, they could secure about 6 meters square for succeeded cases, but they also have like much more obstacle area per clients. So these are the qualitative results for our study. As you can see in these users outside of the space referred, they failed to allocate in that cases. So for analysis, our results show that our method could effectively make a mutual space considering the context of collaboration. And but compared to our method, the simple intersection method mostly failed when the number of client spaces increases. Yes, and our contributions can be threefold. The first is that we first propose the subspace and allocation-based mutual space generation, and also provide the spatial affordance-aware multi-user instantiation algorithm for collaboration. And the last is that we validate our method with evaluation. So the benefit is we could, for more immersive MR telepresence system, or for even a multi-user VR scenario, we can support lean table touch or real walking. The limitation is that we assume we have this floor plan and labels, so which is not adapted for dynamic scene scenarios. And the second is we implemented to the MR Telepresence wishes, but still we have to configure it out how we can to validate the effect of each client have a different interactable spaces. Yeah, that's it for my presentation, and thank you for your attention.
Any questions? So were you thinking some questions? Let me, okay.
Yeah, thanks for the great presentation. Just a short question. So in your algorithm, most of the time you consider the floor plan, right, from the top view, meaning that a height difference is not really taken into account yet, right? Do you have any ideas how one could tackle that? Because eventually, I mean, most of the times tables have a certain height, but this might not always be the same height.
Right.
So I guess this can also lead to some problems, right? If you have a map on a table that is then shown underneath for someone else.
Yeah, that's true. Actually, I mentioned in my paper, but I kind of think separately because I'm more focused on registering some space and locomotive spaces. But there's also another research related with hand pose redirection techniques. So if we get conjugate with that techniques with our method, I think we could overcome the vertical differences between spaces. Yes. Yeah, thank you.
Any other questions? Can you briefly explain how you decide the weight of the objective function again?
So weight it depends on the context of collaboration. So if it's like table-centric scenario, what we have to consider most is how can you align the boundary of the table precisely. So I weighted that as the most primarily effect, and also, of course, consider how much we can secure the movable area in that context as well. So similarly, in the wall cases, the wall surface, how the surface is aligned well is the most primarily considered, and the movable is the objectives. So that was about the spatial matching function. Yes.
So it will be very difficult to optimize find optimized ones.
But currently, so many tools can help me to optimize that weights for navigating for optimal solutions. So I utilize that stuff.
Okay, so time is almost up. Okay, so let's thank the speaker again. Actually, we found out the first speaker could not come, so that we have a video to play at the end. So let's move on to the fourth paper, visual guidance for user placement in Avatar-Mediated telepresence between dissimilar spaces. This is an invited paper of a regular TBCG paper, which authors are Dong-Sek Yang, Ji-Ho Kang, Tai-Hei Kim, and Sung-Hee Lee. Yes, please.
Thank you for the introduction. So the slide is not showing. Hey, my name is Sung-Hee Lee from KAIST, and the first author has already graduated, so I'm presenting the paper. So in this study, we propose a visual guidance method for user placement in avatar-mediated telepresence between these similar spaces. So it's kind of dealing with a similar problem that Dooyoung is also dealing with. The avatar-based telepresence between separate spaces enables users to perceive each other as if they are in the same place through augmented virtual avatars and interact with each other remotely. In this example, when user X is in space A and user Y is in space B, their avatars X prime and Y prime are augmented in front of each counterpart users. So to realize this, the first problem is to find the position for the avatar within the remote space to reflect the user's interaction context. Throughout our study, we assume that the user does not know the layout or the furniture arrangement of the remote space where their avatar will be placed. To simplify the explanation, let's assume that the avatar will be positioned at a point that mirrors the user's relative position to the interaction target, the TV in this case. So in other words, the avatar X prime is placed in the same relative position to the remote TV as the user X is to their own TV. So we see two cases here. So in the first case, the avatar is positioned naturally without any penetration into the environment. In contrast, in the second case, the avatar is placed in a position that causes penetration into the environment, which can hinder the sense of immersion. So both positions are sufficient for the user to interact with the table target, but the resulting quality of the avatar's placement differ greatly. Nevertheless, since the user is unaware of the remote space layout, they cannot predict the quality of their avatar's placement corresponding to their position. Addressing this issue, our study focuses on enabling users to select a position that will lead to a good avatar placement. This study builds upon our previous work on placement retargeting of virtual avatars. In this research, we developed a method to place an avatar in a remote space that is most similar to the user's position, taking into account the geometric relationship with surrounding objects and the other person. The advantage of this approach is that the whole spaces can be used by the user and the avatar for the telepresence. However, not every point of the user space can lead to a good placement for the avatar. We found that there can be positions in the user space that leads to a poor placement of avatar in the remote space, although it's the best placement. The poor placement means the placement that does not maintain the user's interaction context. To solve this problem, we can consider several approaches. First, the user can move freely around their space, and the system positions the avatar at the best possible location, like we did in the previous work. However, this approach cannot prevent users from going to a place that will lead to a poor avatar placement. The second possible approach is that when the user specifies the interacting target, the system provides a single optimal position that enables the interaction and maximizes the avatar placement quality. While this method can maintain good avatar placement quality, it significantly limits the user's freedom of movement. To overcome the drawback of both approaches, we take an approach that visualizes the quality of the avatar's optimal placement for each point in the user's space concerning the interaction target. The user can then choose their preferred position based on the visualized information. This approach ensures the user's freedom while maintaining high avatar placement quality. The main contributions of our work are as follows. First, we propose the first method to enhance the placement quality of remote avatars through information visual augmentation. This allows users to easily select a suitable position for remote interaction and prevents them from moving to a location that are unusable due to spatial differences. Second, we propose a method for positioning the avatar to accurately convey the intent of looking and pointing at the target after the user selects their location. The first step of the study is to develop an avatar placement method that preserves the spatial relationship with the interaction target and avoids environmental penetration. To achieve this, we defined interaction features that describe the spatial relationship between a user or avatar and their interaction target. For the avatar to accurately replicate the user's action of looking at or pointing to a target, the actions of the user and the avatar must be aligned in the same direction relative to the target. To this end, we define the interaction features using the angles between the interacting entities. Specifically, the interaction features consist of a total of 4 angles for a single interaction target. First, there are 2 angles between the user's forward direction and the directions from the user to the left and right edges of the target. Second, there are two angles between the target's forward direction and the directions from the target to the left and right edges of the user. Although the interaction features are composed only of angles, the use of 4 angles that point to the left and right edges of each object implicitly incorporates the distance between the two entities. In the case of multiple interaction targets, features are obtained for each target and concatenated to form the final feature set. Using these interaction features, we can define the similarity between the user and the remote avatar's placement pair. In the left figure, user X is in space A is directly facing the counterpart avatar Y prime. At this point, the user's placement state Q is defined by 2D position and the angle of rotation. Given the interaction target, which is avatar Y prime, we can obtain the interaction features phi Q. Next, for a candidate placement Q prime for the avatar X prime, we can compute its interaction feature phi Q prime with respect to user Y. We define the similarity between the two interaction features phi Q and phi Q prime using a Gaussian kernel. Therefore, the similarity takes a value between 0 and 1. In the figure, the green arrows in space B represent different avatar placements, and the number indicate their similarity values. As shown in the figure, when the relative position and orientation of the two pairs perfectly match, the similarity becomes 1, and it decreases as the positions diverge. We can find the placement that within the avatar space that has the highest similarity, which is referred to as the optimal corresponding placement, in short OCP. In the figure above, the point with a similarity 1.0 is the optimal corresponding placement. We define the recommendation score for a user's placement as the similarity between Q and its optimal corresponding placement. In other words, the recommendation score for a given placement Q is the maximum similarity it can be achieved from the remote space. As we can compute the recommendation score for any user placement, let me explain how to design a visual guide. When the user specifies the interaction target, the system samples possible placements in the user space. In addition, the system removes invalid placements where the interaction target is not visible from the user. Then for each of the remaining placements, the system finds the optimal corresponding placements through optimization and stores the recommendation scores. The figure shows a scenario where a user has selected the avatar as the interaction target. The system samples possible placements as shown as the arrow in space A. Among them, the green placement shows the case that the optimal corresponding placement in space B can maintain the same relative position. In contrast, placement indicated by a red arrow results in the optimal corresponding placement having a different relative position due to the obstacles. As previously mentioned, for the actions of looking and pointing to be accurately conveyed, the direction of the user's and avatar's actions must be aligned with the target. Therefore, a recommendation score closer to 1 indicates a placement more suitable for interaction, while a lower score indicates less suitability. From user evaluation, we determined that the score less than 0.8 indicates invalid placements, while scores higher than 0.8 means a recommendable placement. Please refer to the paper for the detail of the usual study. Next, we designed a visualization scheme that encourages users to consider recommendable placements while discouraging them from considering invalid placements. We adopted a color-coded fan shape as a visual indicator, as shown in the left figure. So invalid placements with a recommendation score below 0.8 are colored red, while those above 0.8 are shaded from yellow to green. Additionally, we optionally visualized digital replica of objects in the remote space in transparent blue to give a visual cue of how the remote space objects are arranged. The digital replica are aligned with respect to the interaction target. Next, we conducted a VR experiment to verify whether the proposed visualization technique effectively guides the users toward placements with high recommendation scores. The experiment was conducted as follows. First, the system randomly assigned our interaction target to the user and provided various combinations of visualizations. The user was then asked to use the visualization to select and move to a position suitable for interacting with the designated target. Once the movement was completed, the system records the recommendation score of the user's chosen placement. The VR experiment was conducted with a total of 4 space pairs, 2 meeting room and meeting room pairs, and 2 meeting room and personal room pairs. The visualization combinations were presented with 4 types. First, a baseline with no visualization. Second, a method that shows only the invalid placements. Third, a method that displays both the invalid and recommended placements. And finally, a method that adds remote space layout to the above. We conducted experiments based on these 4 visualization combinations, and the target interaction targets included only avatar or screen or both. The experiment was conducted with 16 participants. Each participant responded to a total of 64 samples. The left graph shows the distribution of the recommendation scores of the user selected placements for each visualization. As more visualization elements are added, the range of recommendation scores becomes narrower and the median increases. The right table shows the result of a pairwise test comparing visualization combinations. Except for the last case where remote space layout is added, all differences were statistically significant, and the trend shows that the recommendation score increased as the more visualization elements are added. Although the remote space layout did not have a significant impact on recommendation scores, many participants reported that it helped them better understand the configuration of the remote spaces. Lastly, we conducted an AR experiment to verify the effectiveness of our approach in a real remote telepresence environment. The participants in the 2 spaces take turns to select the interaction target and move according to the visual guidance, which subsequently determines the placement of their avatars.
Welcome to my place, and thank you for inviting me to your place.
Hi, welcome.
Today, I'm going to present about visual guidance for telepresence. Could you please stand in front of the TV?
Sure.
And they are setting the interaction target. And after setting the interaction target, it shows the visual guide. And she selects one of the green marks, which shows that indicates the good after placement. Now the user X selects the interaction target. Then the system shows the good placement candidates. So after positioning, the avatar is also placed, and they can communicate.
Okay, I'll start.
All right, so on behalf of time, I just cut it here. So we compared our method with a baseline method which places avatars such that they maintain the user's relative position with respect to the interaction target. We found that our method decreases the penetration between the avatar and environment, increases the sense that the avatar is aware of the objects. In addition, we confirmed that our visualization was useful and helpful for the users. One disadvantage of our method is that it tends to increase the visual overload. To summarize, we presented a novel visualization method for the user's placement that will ensure that quality of avatar placement in the remote space. Our work has been validated by both VR and MR experiments. There are several interesting future research directions. Our system assumes interaction between the 2 users. As the number of users increases, the complexity of the problem can increase. It remains to tackle this high degree of complexity with many users. As we narrow down our target scenario to remote meetings, space categories were limited to the conference and private rooms, and only gaze and pointing interactions were considered. We need to validate and extend our method for other application scenarios, including, for example, interactive learning and remote collaboration with object manipulation. Lastly, we are presenting a really cool work for telepresence between different spaces at the demo session, so please check out the demo as well. Thank you for your attention.
Do you have any questions?
So everything is clear, right?
So can you explain again about the score? How do you optimize the location?
Right. So the score was compute it.
Is the spatial layout considered or only the 2D layout only?
Oh, right. So we, in this case, we only consider the 2D layout, the floor plan. So if there is a difference between the height, then probably the score should be extended, right?
Is it a trivial extension, or do you have any challenge, the difficulty in taking to take the 3D information into account?
Yeah, I don't see like a significant increase of the challenge. It's probably just an extension of one dimension, I think. Yeah.
Any questions?
Hey, let's meet at the demo session then.
I see the visualization very nice and cute and useful, but at the same time, it might be a bit, congested, a bit busy for casual use. Do you want to decrease the amount of the information, or do you need to show everything in a grid?
Right. So for the visualization, we considered the several the candidates. So one thing is that the one problem we face is that the user cannot see the visual guide if it's occluded by the real object. So that's one thing. So we have thought of like showing kind of a pillar kind of things instead of just markers on the floor. But that proved not very user-friendly. So we decided not to use it. And finally, we just chose to use that fan shape. But still, we found out that that gave a pretty big, visual overload to the user. But then one thing is that once they determine their position, they just turn off the visualization so that they can return to the original, interaction. Yeah.
I see.
That's a very good question. So actually, yeah, that was one option, and we tested that. And that's actually one of our experiment element. But probably you might have not seen it clear because we presented that obstacle as a very a transparent object. And users reported that actually presenting that obstacle helps them to understand the remote space layout. So it's good, but the problem with that showing the remote space obstacle is that if you have more than one interaction targets. For example, in here, we used only TV as an interaction target, but if you have more interaction targets, then the question arises whether, like, how to visualize that obstacles, like where to visualize the obstacle. That becomes kind of a complex problem. So that might give a challenge. Yeah. Thank you.
Okay. So let's thank the speaker again.
Thank you.
Okay, let us get back to the first paper, which is actually online. I have a YouTube video, and the author is waiting at the Zoom, so let me connect.
Hello everyone, my name is Nelusha Wattaranthenne. I recently completed my master's degree at University of British Columbia, Okanagan campus. My co-authors are Marium-E Jannat, Dr. Khalad Hasan, and Dr. Patricia Lasserre. Today, I'm going to present our work on exploring the effect of weaving attributes of mobile augmented reality interfaces on remote collaborative and competitive tasks. As you may already know, mobile augmented reality, or MAR, is a technology that allows users to simply pull out their personal devices, such as smartphones, and augment virtual content into the real world. For example, using the IKEA Place application, users can augment furniture into their new house without actually purchasing them. Additionally, the popular games like Pokemon Go allow users to find and catch virtual creatures in a real environment. Even though most of the commercially available applications focused on a single user, researchers identified augmented reality can be used in multi-user settings as well. Hence, the prior work on MIR can be categorized into co-located and remote experiences. Wells and his colleagues explored how mobile augmented reality interfaces facilitated co-located group experience while games like Swiftshot and Brick were focused on co-located multiplayer experience with the augmented content. On the other hand, there have been research work done to facilitate remote MR collaboration. Similarly, Magic Flowerpot and Magic Players, though all users are not physically present in the same place. To the best of my knowledge, majority of the currently available remote AR solutions require extra devices like head-mounted displays or PCs to facilitate remote collaborative experience to the users. Therefore, little to no work has explored how remote engagement can occur when both remote and local users utilize handheld devices, and how their perspectives, manipulation, and spatial awareness can impact task completion for both competitive and collaborative tasks. Therefore, we designed and developed a prototype mobile application with 5 different techniques consisting of a combination of different content viewing attributes. And then we conducted a comprehensive user study to explore the impact of these techniques on remote collaborative and competitive environments. Lastly, we present a set of design recommendations to improve remote MR experience in future. In the prototype AR application, we use AR markers to augment virtual content to the user's mobile devices. User can visualize the virtual content in their mobile device from their own perspective. They can control the model manipulation synchronously or asynchronously. As in this example, the user 1 can see the other user's view on a small screen from their own perspective. In addition, users can add arrow annotation to directly show the exact place of the virtual model they are currently looking at. We used 2 simple virtual models for our experiment. A city model with different colors of cars randomly placed in the model, and a 3D cube with different colors of triangular and square faces. Subsequently, we designed 5 different techniques named based on their content viewing angle, model manipulation type, and the view type. In the next few slides, I will discuss how these 5 techniques differ from each other. The technique 1, SSP, which has the same viewing angle based on the user who has the control of the model currently. For example, now the user 1 have the control and user 2 see the virtual cube exactly as the way user 1 sees it. It is similar to the city model as well. In this technique, user can view the virtual content in their own perspective. But the model manipulations are synchronous as well as they can see the content using their own personal view. In this technique, although the users can view the virtual content from...
I'm really sorry about the technical issues, but I will put the link to this YouTube video on the Discord so that you can check the video later. And also the paper has the information of the also the contact so that you can send questions directly. Thank you very much.